Before we talk about how the brain can drive motor action, let's talk about movement that happens without the brain's involvement. Let's start with motor activity arising from two sources: the dorsal root ganglion cells of the sensory system and the spinal interneurons. These two forms of input need not engage with higher brain areas at all. Rather, they can drive lower motor neuron activity entirely using circuit intrinsic to the spinal cord. The motor output of this intrinsic circuitry is reflexive, short, automatic, and involuntary responses to sensory stimuli that occur without conscious control. Spinal reflexes are the body's fast, closed-loop control system. They can deal with threats too urgent to allow for the comparatively slow flow of information through cortex, and they can provide for fast, in-the-loop control processes like balance, freeing up the cortex to spend its time organizing complex, goal-directed behavior without constantly having to attend to new sensory stimuli. Spinal reflexes are controlled by the input from the dorsal root ganglion cells that respond to sensory stimulation from the environment. These dorsal root ganglion cells synapse either directly onto a motor neuron or act through spinal interneurons to coordinate the motor neuron activity involved in reflexive action. Through just a few intrinsic spinal circuits, dorsal root ganglion cells and spinal interneurons work together to coordinate many of our daily behaviors. One of the simplest and best understood reflexes is the myotatic stretch reflex, often simply referred to as the stretch reflex. The myotatic stretch reflex is most clearly seen when an unexpected load is placed on a muscle. Its key function is to resist the lengthening of a muscle. In other words, when a muscle is stretched, the myotatic reflex circuit will lead to a corrective contraction of the same muscle. Such corrections keep you standing upright and able to deal with sudden, unexpected weights at an automatic, subconscious level. Consider, for an example, a person standing upright who then begins to lean to one side. The postural muscles on the side the person's leaning away from will stretch. Thanks to the myotatic stretch reflex, stretch receptors in these muscles will sense this and lead those same muscles to contract to correct posture. Further, consider a waiter holding an empty tray on which someone suddenly places a glass of water. The waiter's muscles are not generating force to support the weight. If not for the myotatic stretch reflex, the tray would drop. However, thanks to the myotatic stretch reflex, the muscles required to bear the weight of the tray immediately contract, preventing the waiter from dropping the tray and glass. How does this happen? Amazingly, this instantaneous adaptive behavior requires just a few key circuit elements to function. Specifically, when a muscle stretches, the stretch is detected by a sensory organ called the muscle spindle, buried deep within the muscle fibers. The muscle spindle is part of a class of sensory organs known as proprioceptors, which get their name from the Latin proprius, which means own. This is an appropriate title since proprioceptors are concerned with monitoring the state of your own muscles and detecting changes in muscle length and tension, which allows you to get a sense of the location of your joints, which are positioned by muscle movement in space. Muscle spindles are spindle-shaped structures located deep within a muscle mass. They're composed of 6 to 8 thin muscle fibers called intrafusal muscle fibers. Unlike extrafusal muscle fibers, which, as you'll see, do the work of the muscle, these thin fibers don't contribute much to the muscle contraction or extension. Rather, they report on two characteristics of a muscle: its length and its rate of change in length. This report is conveyed to sensory dendrites wrapped around the intrafusal fibers. These sensory dendrites come from the dorsal root ganglion cell bodies, whose axons, as you already know, synapse onto the alpha motor neurons in the spinal cord. The proprioceptive report comes in the form of a stretch of the intrafusal muscle fibers, which occurs when the muscle mass itself is stretched. This stretch opens mechanically gated ion channels in the wrapped sensory dendrites, which causes ions to rush in, depolarizing the dendrites and generating an action potential in the cell. The action potential in the dorsal root ganglion cell is carried through its afferent nerve fiber all the way to the spinal cord, where it synapses on an alpha motor neuron. Generally, this alpha motor neuron will innervate the same muscle in which a stretch was detected. Activation of the alpha motor neuron will induce an action potential in the neuron, which will course down its axon and cause its target muscle fibers to contract. Since the muscle fibers lie on the same muscle that generated the stretch signal, this is a corrective action. This is how the stretch reflex is able to automatically regulate skeletal muscle length through a quite simple mechanism involving only a few neurons. Its simplicity is actually key to the effectiveness of the stretch reflex. Because the stretch reflexes are monosynaptic, meaning that there's only one synapse between incoming information and the outgoing signal that keeps the muscle's length constant, the entire reflex arc, from initial stretch sensation to muscle contraction, takes only about 1 millisecond. And most of that time, about 0.5 to 0.9 milliseconds, is taken up by the single synaptic delay. If another synapse were added to the myotatic stretch reflex, it would take twice as long to adjust for a stretched muscle. The stretch reflex allows weight-bearing muscles, like the quadriceps in our upper thighs, to adjust to the changing load at the level of the spinal cord, without having to engage the brain in this low-level decision-making. However, there is one problem with this highly adaptive circuit. When the muscle mass stretches, both intrafusal and extrafusal muscle fibers stretch. As you now know, this stretch cues corrective action in alpha motor neurons that contracts the extrafusal muscle fibers, bringing them back to their original length. But what about the intrafusal muscle fibers? Alpha motor neurons don't synapse onto them. They're not correctively contracted in this myotatic stretch reflex. However, as the muscle mass around them contracts, you can imagine these stretched out fibers becoming loose, hanging limp like spaghetti in their muscle spindles. Such loose fibers would be useless in detecting subsequent muscle stretches, so your body doesn't allow the intrafusal fibers to reach this limp spaghetti state. The length of the intrafusal muscle fibers is adaptively reset by another sensory motor circuit. Specifically, when a muscle stretches, sensory dendrites wrapped around the ends of the muscle spindle also detect the stretch. These dendrites, called secondary afferents, as opposed to the primary afferents discussed in the stretch reflex, synapse onto a second class of motor neurons in the spinal cord. These are the so-called gamma motor neurons, and they innervate the intrafusal muscle fibers themselves. An impulse in the gamma motor neuron causes the intrafusal fibers to contract alongside the contracting extrafusal fibers, and thus to remain taut and able to detect further stretches.